Welcome, biology grad students. I know you're grinding away in the lab every single day, so first off, huge respect for the work you do. But hey, let's be honest for a second. Have you ever looked at the analytical machines on your bench and felt like they're just magic boxes? You put a sample in, data pops out, but what's actually happening inside is completely invisible? Well, today, I'm going to act as your senior lab mentor. We're going to completely demystify the physical rules hidden deep inside your everyday lab equipment. We're going to read the optical blueprint together. So let's dive right in. Here's our game plan for today. First, we'll tackle the black box problem head on. Then we'll grab our master key, the fundamental equation of light. From there, we hit a fork in the road, exploring path 1, light as a wave, and path 2, light as a particle. Finally, we'll open up the biomeasurement toolbox. And don't worry, we're not getting bogged down in crazy math. We're going straight from abstract concepts right to the practical gears sitting on your bench. So here's a quick question to kick things off. When you turn that wavelength dial on a spectrophotometer or tweak the intensity knob on your microscope, what are you actually doing? Sure, you know the numbers change on the screen, but can you physically picture the interaction happening inside that machine and inside your sample the moment you turn that dial? For most of us, these devices are incredibly frustrating black boxes. You know the input, you know the output, but the middle is just a total mystery. But what if we could reverse engineer that? By using a simple optical blueprint, essentially translating the physics of light into a language we intuitively understand, we can turn that opaque black box into a completely transparent glass case. Okay, moving into section 2, the master key, translating the equation. Let's grab this single foundational concept that's going to guide this entire explainer. Now, this might look like a scary plane wave equation, but here's the really cool part. It's actually just the dials you touch every day. Think of it like this. Amplitude, or A, is literally just your brightness dial. Angular frequency, the omega, controls the speed and time. That's your color dial. And the wave number, K, is the spatial density, which essentially acts as your resolution ruler when you're looking at cells. See? It's not abstract math. It's literally an operating manual for your equipment. And here's where it gets fascinating. In the world of light, space and time are locked together like gears. So what happens when light travels from a vacuum into biological tissue, like a cell? Well, the light actually slows down, and its wavelength gets squeezed shorter. But the other gear, the color or temporal frequency, stays exactly the same. That physical distortion of light inside the cell, that is exactly the biological signal we're trying to measure. Now, you've probably heard of the wave-particle duality of light. People treat it like this mind-bending paradox, but honestly, it's not. It's just a simple fork in the road, separated by Planck's constant. It just depends on what we want to look at. If we focus on spatial density, we take the wave path. If we care about the speed of time and how energy is exchanged, we take the particle path. It really is that simple. All right, heading into section 3, path 1, the wave nature of light. Let's take that first path and track the light's direction and overlapping shapes. First up on this path is scattering. If you want a visual, imagine a microscopic game of billiards. The light is the cue ball, bouncing off molecules inside your cells and ricocheting in all directions. But not all bounces are the same. If light hits a massive particle, like a whole cell, it bounces straight forward without losing energy. That's called me-scattering, and it's exactly why your cell suspensions look milky white. On the flip side, we have inelastic Raman scattering. This is where the light actually loses a tiny bit of energy to the molecular vibration of whatever it hit. That lost energy changes the color slightly, giving us a unique, highly specific fingerprint for that exact molecule. It's a hugely powerful tool. Next up is polarization. Think of this as twisting wavy ribbons of light. It's all about the direction the wave is vibrating. It basically acts like a microscopic antenna feeling out the specific shape of your molecules. Here's how we use it in the lab. Linear polarization, where light only wiggles in one straight plane, is perfect for measuring the thickness of thin films, which is what ellipsometry does. But what about circular polarization, where the light moves forward like a twisting corkscrew? Well, that corkscrew shape maps perfectly onto chiral or asymmetrical molecules like amino acids. This is the exact principle behind CD spectroscopy. Our third wave property is interference. This is all about how crowds of waves interact. Think of a laser as a highly synchronized, well-behaved crowd marching in perfect step. But broadband white light, that's a chaotic, badly behaved crowd constantly bumping into each other. When wave peaks align, they amplify each other. When a peak meets a valley, they cancel out. The key metric here is coherence length. Remember our badly behaved crowd? It has a super short coherence length, meaning it only interferes over a tiny specific distance. But guess what? We can use that. It acts like a pair of precise nanoscale tweezers, letting us extract a very specific depth slice of biological tissue. That's the sheer brilliance behind OCT imaging used in ophthalmology.
Okay, Section 4, Path 2, the particle nature of light. Let's completely shift gears here. This is where we stop looking at waves and start treating light as discrete packets of energy.
I know terms like quantum states sound intimidating, but let's completely reframe the famous Jablonski diagram. Forget the heavy physics for a second. It's literally just a household account book for molecular energy. In this economy, photons are the currency. For a molecule to move up to an excited state, like the upstairs of a house, it has to pay exact change. That's absorption. Once it's up there, it wanders around and drops some loose change as heat, which we call vibrational relaxation. Finally, to jump all the way back down to the ground floor, it spends whatever energy it has left emitting a red-shifted light. That is fluorescence. The budget perfectly balances every single time.
And how do we quantify that absorption? Good old Beer-Lambert law. Think of it like fishing. You throw a net, which represents the molar absorption coefficient, into a river of photons. The length of the river is your path length. By simply counting how many photons passed through versus how many got caught, you can calculate the exact concentration of your target sample. It's brilliant, right?
But when we talk about particles of light, we have to talk about noise. At really low light levels, light gets inherently grainy. This is called shot noise. Imagine rain dropping into a bucket. If it's just a light drizzle, the drops are random and sparse. Because of this random Poisson statistic, if you want to double your signal clarity, you can't just double your time. You literally have to observe for 4 times as long. That's just a fundamental physical limit you can't avoid. And finally, Section 5, the grand finale, your optical toolbox. Let's bring all this physics out of the textbook and connect it straight to the gear sitting on your lab bench right now. Here is your master blueprint, the integration matrix. This shows exactly how every single wave and particle phenomenon we just talked about maps directly to a parameter that you can hack in the lab. Let's lock this checklist in. If you're measuring optical density or using NIRS, you're hacking wave momentum. If you're doing CD spectroscopy, you're manipulating phase differences and twists. OCT, that's wave coherence length. And if you're using a spectrophotometer or a fluorescence microscope, you've completely switched to the particle model. You're tracking exact energy budgets and lifetimes. We've officially connected the physics to the hardware. As you've seen today, holding this optical blueprint changes everything. It takes the incredibly chaotic, complex world of biological phenomena and translates it into hard, quantifiable data. You're no longer just turning random dials. You're actively engaging in a dialogue between light and matter. So, I'll leave you with this. Now that you're armed with the optical blueprint, what are you going to do with it? Tomorrow, when you walk into the lab and stand in front of that microscope or spectrometer, I want you to look at it differently. There's a whole universe of physics happening inside that metal box. How will you use these tools to peel back the veil of life's complex mysteries? I absolutely can't wait to see what you discover. Catch you next time.